Okay, so welcome back, everybody. This is our first day back since the test, and I hope you're feeling pretty good about how you did. If you don't feel so good about your test score, there is a way to improve that situation, which is to do the test corrections. So basically, if you want to do test corrections, on Tuesday, you're going to submit the following to me. Any problem that you missed, just do it on separate paper, and then staple that to the back of your original test. I'll regrade it. And if you get all of the questions right that you missed, you can get up to 1/4 of the points that you missed back in the corrections. Okay? So, any questions on that? If you didn't collect your test yet, just come get it from me at the end of the class. Okay? The other thing is the next homework assignment, which is number 7. That's going to be due next Thursday. So for the next couple assignments, homework 7 due next week, and then homework 8 the week after that, we're going to move the due date to Thursday, and then when we come back from the break, spring break, we'll go back to our usual assignment due dates being Tuesday, okay? So this one involves a worksheet. You can find it up here, and some problems from the textbook. Any questions on all that stuff? Okay, so let's get into the new material. We're going to begin a pretty long unit on Newton's laws of motion. We're going to be on this for over a month. Now, this is going to come into 2 chapters. The first chapter is chapter 5 of our textbook, which is just sort of a basic statement of what the laws of motion are. And then in chapter 6, we'll get into some of the applications. But throughout those 2 chapters, we'll spend about a month on this material. So let's start with some really ancient kind of like folk ideas of physics. So I want to tell you about sort of a theory of physics that was developed by Aristotle. Now, of course, Aristotle is an ancient Greek philosopher. He was not the first person to think about physics ideas, but I'm just kind of posing this to you as an example, okay? This is an ancient set of ideas about physics that it turns out is wrong, but it's helpful to see how we got from these wrong ideas to where we currently are now, okay? So, has everyone heard of Aristotle's Physics, where the idea is there are 4 natural elements, earth, fire, water, and air? So the idea back then was everything is made out of those 4 fundamental pieces in some kind of mixture, okay? The other idea was that each one of these natural elements has what's called a natural resting place, where for earth, the natural resting place is as low as possible, then water, then air, and then fire. Those tend to rise up. So the idea would be, if you want to explain how anything moves, it just moves towards its natural resting place. And then the idea would be, if you want to move something away from its natural resting place, like pick something up that's made out of mostly earth and move it up like this, it's going to take some effort. But then if I let go of it, it's going to fall back down. Okay? So these are incorrect ideas. We know now that if you look at this periodic table of elements, that's really what the world is made up of, not these 4 elements. And motion is a little bit more complicated than what's summed up in these 2 rules. So how do we go from this to something more modern? Let's skip ahead about 2,000 years to Isaac Newton. So in a sense, Isaac Newton was the first person to really get this stuff right in a quantitative way. And what we're going to learn about are the laws of motion developed by Newton. But let's really have a roadmap as to where we're going with this kind of thing. Up until this point, for the last month or month and a half, we've been talking about kinematics. And so remember, when I use the word kinematics, I'm just referring to a description of motion. I'm just describing how something is moving around in terms of its position, its velocity, its acceleration. That's what we mean by a description, okay? But dynamics, which is what we're going to start to get into with this chapter, it deals with the underlying causes of motion. So we don't want to just merely describe how something is moving, but we want to know why it's moving in the particular way it is. And as it turns out, the causes of motion in this framework we're going to learn about is forces. So forces are the things that set objects in motion, and if we understand forces, we can understand why things move the way they do. So here is the basic outline of how dynamics as envisioned by Isaac Newton works. Okay, I'm going to try to describe this in the most broad, general possible way. So if we analyze the forces that are acting on an object, if we understand every single force that is pushing or pulling on some object, and we have an exact description of those forces, we can use that to calculate the acceleration of that object. Okay? And then if we have its acceleration, and we also know its starting position and its starting velocity, so we know how it's accelerating and how its motion starts off, we can then calculate how it's going to move anytime later. We can calculate its velocity anytime later. We can calculate its position anytime later. And this is a really powerful framework because it essentially allows you to predict the future behavior of any system as long as you know the forces acting on it. Okay? So this could be something really simple, like just me pushing this stack of papers across the desk. If I know the force I'm applying, I can describe how the stack of papers moves. But it could also be used for something much more complicated. Let's say the orbit of an asteroid around the solar system. So it's really, really broad. We can use this for pretty much any situation you can envision. Okay, so are we clear on where we're going? Okay, so there are 3 laws of motion, and we're going to take them in order, starting with the first law. Does anyone know off the top of their head what the first law says? You may have heard this before. Yeah, it's pretty much that. Objects in motion tend to stay in motion, but there are some subtleties to it. There's a little bit more going on than that. That's the correct statement, but there's more to say about it, so we're going to get into that. So before we build up to the first law, it's going to involve this idea of force. So let's actually figure out what force is. So let's define force in a really kind of intuitive way. For our purposes, force is just any kind of push or pull that's exerted on an object. Now, right away, we should be noting that force is a vector quantity because when you apply a force to something, it matters what direction you apply that force in. It's a different situation to push the stack of papers this way or that way. So the direction matters, therefore it's a vector. Let's also notice that you can exert multiple forces on an object all at the same time. Doesn't necessarily have to be the case that there's just a single force acting on an object. Oftentimes, you're going to have a whole bunch of forces acting all simultaneously. And so when we add up all of the different forces that are acting on an object, what we call this is the net force. Okay, so this idea of the net force, adding up all the different forces, is going to be really crucial. So let's just talk about how this is notated. So when you see this symbol right here, what does it mean? This is a summation symbol. So summation over F, that's the sum of all the forces. That's what we call the net force. So this means add up force number 1 to force number 2 to force number 3 until you've included all the forces. That's what that means. Okay, sometimes what we'll use to sort of have a picture of the forces being acted on, or that are acting on an object, is this thing called a free body diagram, where we show the object, and then using arrows that are coming off the object, we indicate the different forces acting on the object, okay? So remember, the arrow, the way it's pointing, is telling you about the direction of a force. So force number 4 is going straight up, for example. What does the length of this arrow tell us about a force? Tell us the magnitude. So it's how strong is the force you're applying. That's what the length of the arrow is saying. Okay, so one last thing to say about this. There will be situations where when you add up all the forces acting on an object, you get 0. So the net force acting on an object can be 0 in certain situations. And when that's the case, we say that all the forces are balanced, because any force that's apparent there is going to be balanced out by some other force that's also present. Okay? So that's just a little bit of terminology and the way we draw things on graphs and the way we notate things. So any questions so far? So we're going to keep it moving, and what I want to do here is get you thinking about the first law, or what's going to lead us up to the first law. Okay, so as we know, if you have a block and you push it along a table, eventually it's going to come to a stop, right? And the reason for that is there's friction between the underside of that block and the table. So this is the kind of situation you should be envisioning, that sort of motion. We give the block a push, but then it comes to a stop because of friction. But we can obviously reduce friction. Maybe we can make the two surfaces more smooth. We could sand them down, polish them, maybe even like add some kind of lubrication to them. And in that case, what would happen is it would just take longer to come to a stop. So it would slide and then maybe come to a stop over here, okay? So you get the idea, that it slides farther, the less friction there is. So my question for you is, let's suppose this table were infinitely long, so it never would fall off the table, it would just keep going if it could, and we could eliminate all friction and all air resistance. So we give this block a push, what happens to it? It never stops, right? The only thing that's causing the block to stop is the fact that there's this force, which we call friction, acting on it, okay? If there is no force that's impeding its motion, that is, we reduce friction and actually air resistance entirely, then there's no reason it would come to a stop. You see what I mean? So if there's a complete balance of forces happening, then this thing will just continue on at a constant velocity. And that's really the idea behind the first law. Okay? Is that making sense? So let's state Newton's first law. Newton's first law says that an object moves at a constant velocity unless it's acted upon by an unbalanced force. Okay? So if all the forces are perfectly balanced out, there's zero net force, in other words, then that object is going to be moving with a constant velocity. Now, one thing you should note is that when I say constant velocity, that could also mean zero velocity, right? If something just has zero velocity and it stays that way, that's also a constant velocity. But it also could refer to a non-zero constant velocity. So let me give you two conceptual examples of this, okay? So the first one is this. Let's imagine this rock that's being pushed in two different directions by these two different people. And let's suppose that the two forces they're applying are exactly equal. So what we'd have is a balance of forces, right? If we were to consider the net force acting on this thing, we would say it's zero. So this is an object that is not going to accelerate. Okay? And it makes sense that it wouldn't accelerate intuitively, right? But let's say instead of pushing in opposite directions so that the forces cancel out, they push in the same direction. So now there's actually a net force going to the left. The forces are unbalanced in this case, is what we say, and the rock can accelerate in this situation. Okay? So here's another example. You're driving down the street in your car at a constant speed, and then suddenly you hit the brakes. And one thing you notice if you've ever done this before is you seem to kind of fly forward until your seatbelt catches you. Why is that? Well, your body was already moving forward at some velocity, right? It's going to keep moving forward at that velocity until some force acts on your body to stop it. And that force is provided by the seatbelt. So you're going to basically keep moving forward in your seat until the seatbelt catches you. And that's why it kind of feels like you're being lurched forward in your seat. Okay? Does that example make sense? Okay. Here's another example. This actually can be explained with the first law. So don't ever do this, but if you have a glass of beer, you do this, you fling it forward, the beer flies out of the glass, you can splash it on someone, right? Why does that happen? Try to use the ideas encapsulated in the first law of motion to explain this. I just want to see if anyone out there has an explanation they want to throw out. Yeah?
When you launch it forward, the beer continues moving forward and therefore hits someone up.
Yeah. So, okay. So you're exerting a force at first when you're pushing the beer forward, right? The bottom of the glass is exerting a force on the beer. And then starts to move at some velocity, and it will continue to move at that velocity until some force acts on it to bring it to a stop. And that happens to be the person's face that brings it to a stop, right? So this is just another example of the first law. Does that make sense? Okay. So hopefully that's pretty straightforward and pretty clear. Now what I'm going to do is show you sort of a complication to this whole thing, okay? The first law is not just as simple as what we've been saying here. It's not just that an object will have a constant velocity, an unchanging velocity, unless some kind of force acts on it. There's a little bit more going on, okay? And so I want you to think of this example. So let's say we have a truck that's carrying an unsecured box. And when I say it's unsecured, it's not strapped down in the back of the truck. The back hatch of the truck is open, so it can slide out. And let's also say there's no friction that would hold it in place either. So it's just completely unsecured. Meaning, if the truck starts to move, it's going to just slide out the back. Okay? But what I want to do is look at this situation from two different points of view. Okay? One of those points of view is what I'll call the ground frame of reference. That's what someone just standing on the side of the road would see. So that's the coordinates x, y right here. And then the other point of view I want to think about is this one that's moving with the truck. So we've got the ground frame of reference, we've got the truck frame of reference. Let's just look at this situation in both points of view, starting with the ground frame of reference. So I'm going to show you an animation, okay? Watch this. That's pretty sensible, right? So what just happened? There was no force acting on this box to the right or to the left, nothing in the x direction, right? And so therefore it didn't accelerate in the x direction. And it didn't move with the truck, it just slid out the back. That's pretty much compatible with the first law of motion, right? Because if you think about it, again, no force in the x direction, and it did not accelerate in the x direction. That's what we'd expect, because it should just keep its constant velocity of 0, because it's not moving, if that's the case. Does that make sense, everyone? Okay. But let's see the same animation from this point of view. So take the perspective of someone riding in the truck, okay? And you see the box basically fly out the back, don't you? So from your perspective, did the box accelerate if you're in the truck?
Yeah.
Yeah, it did, right? It accelerated backwards, right? If you're in the truck, you say the box accelerated backwards. This is what it looks like. Okay? That's the perspective of this observer in the truck. Let me just show you one more time. So that's what someone on the ground sees. Box didn't accelerate. Someone in the truck sees, looks like the box did accelerate backwards. Isn't there a problem with that? Because according to Newton's first law, if there's no force that's pushing it that way, it shouldn't be accelerating that way, right? So what's going on? In the truck's frame of reference, the box did appear to accelerate in the minus x direction, but there's no force that we can identify that's causing that to happen, right? So is that a violation of the first law of motion? No. Okay, well, it's not, but we're going to see why, okay? Okay, this brings us to a kind of tricky topic, but the thing I really want to emphasize here is that you have to be a little bit careful when you start writing down Newton's laws of motion, okay? This brings us to the point of inertial reference frames. Okay, now don't even write this equation at the bottom of the slide down. Don't even worry about this. I'm just using this to illustrate a point, okay? Let's start up here. An inertial reference frame is a reference frame that is not accelerating. So it's a set of coordinates that you use to measure motion that is not accelerating. So in the previous example, the ground frame of reference would be an inertial reference frame, okay, because it's not accelerating. But the truck's coordinates, the x prime, y prime coordinates that you saw moving with the truck, those would be what we call non-inertial, because that set of coordinates is accelerating. Okay, so there's a difference between a frame of reference that's accelerating, we call that non-inertial, and one that is not accelerating, we call that inertial. So the point here is Newton's laws of motion, all three of them that we're going to learn about, are only valid if we're using an inertial reference frame. Okay? Only if we're using a set of coordinates that is not accelerating to measure the motion. Okay? So let me give you an example of how this plays out in the second law of motion. So we haven't even gotten here yet. We're going to get here in more detail later, but this is just to illustrate a point. Newton's second law takes on this form that you may have seen before, F equals ma, as long as we're using inertial reference frames to measure motion. We're all familiar with this equation? Okay, let's say I am using a non-inertial reference frame. This is what that same F equals ma formula looks like. So you have mass times acceleration, just like here, but then you have all these extra terms. And these terms are just there to account for the fact that you're trying to do physics, you're trying to describe motion in a non-inertial reference frame, in an accelerating reference frame. So needless to say, this equation up here is much more simple than this one down here. Which is to say, we always want to be working in this kind of reference frame and not this one. So it is possible to work with this equation, but we're just not going to do it in this class, okay? By the way, these extra terms are sometimes referred to as fictitious forces, okay? But again, we're not going to be dealing with this. So let me show you a video that will hopefully make this a bit more intuitive, okay? So in this video, we're going to be looking at two different frames of reference. And what we're going to be looking at is a game of catch, just two people throwing a ball back and forth, okay? At first, we're going to see the game of catch in the ground frame of reference. So they're just throwing a ball back and forth. Everything looks pretty normal. But then we're going to see that same game of catch played on a rotating platform. So they're going to be both spinning around and trying to play catch. And as you'll see, some weird things start happening. So let's just take a look at the video and explain what's going on. So this came from MIT. You can watch the link down here. Okay, so this is the platform I talked about. It's not rotating for the moment. And they're just playing catch. Pretty straightforward, right? All right, so now what we're going to do is get this platform rotating. Like this. And as you can see, they're having a hard time even throwing the ball right. If you try this out, you'll see it is pretty difficult to actually make an accurate throw. So let's observe this from the ground frame of reference, okay? The camera is not rotating with the platform. Look at how the ball is moving. It moves in a pretty normal trajectory, right? It's not curving one way or another. Just take a close look at that, right? The ball is not moving in a way that looks unfamiliar to us, right? Okay? But let's take a look at this same situation with a camera that's actually rotating with the whole platform like this. What do you see happening now? See the ball kind of appears to curve away? Like that? Let's see it in slow motion. Okay, the point I want to emphasize here is that the ball did not curve away because there was some force pushing it that way, okay? There was no force pushing it that way. It's just that you're on a rotating platform, which is a non-inertial reference frame, okay? And physics works a little differently when you're in a non-inertial frame. So that's what it looks like kind of from the POV, right? Yeah, and if you rotate it in the other direction, you'll actually see the ball kind of curves the other way. So this effect that we're looking at here is called the Coriolis effect, if you want to know a little bit more about this. We're not going to cover this in this class. The math is a little bit beyond the scope of this class. But again, this is just to illustrate the difference between physics in an inertial and a non-inertial reference frame, okay? So do you have any questions about what we just saw, just conceptually? It's a little bit tricky. Yeah.
Do the equations work if the frame of reference is moving at a constant velocity, or is it?
Oh yeah, so if you're moving at a constant velocity, that's no problem. It's just accelerating frames where the equations have to change a bit, okay? Now let me ask you this, everybody. What about the Earth? I mean, we're on the Earth right now. We're on a rotating reference frame, aren't we? So you might expect that some of those weird effects that we saw for the rotating platform should be coming into play for any motion that's based on the Earth, right? Like if I were to throw a baseball towards you, it should kind of hook one way or another because the Earth is rotating, right? Does that happen? It actually does happen. It's just the effect is super subtle. It's a very small effect when it comes to Earth-based motion, okay? You can usually ignore that sort of thing, okay, under most everyday circumstances. So for example, if I were to toss you a football from across the field, this Coriolis effect that makes the ball kind of curve is pretty negligible, but it is there. If you had really precise tools, you can measure it. And if you were trying to do something with really, really high precision, you would have to account for it. And you know, in the military, they actually have to account for this a lot. But we're going to ignore these effects because they really complicate the mathematics and they tend to be very small effects anyway, okay? So what's the point of all this? Yes, the Earth is not an inertial reference frame because it's rotating, but to a pretty good approximation, we can treat it as inertial because these fictitious forces, those extra terms in our equations, are typically very small, okay? So from here on out, we're going to treat the Earth as an inertial reference frame, even though it's sort of an approximation, okay? And in most circumstances, that's a very good approximation to make. All right, any questions so far? Okay, so there we go. So what I'm going to do is start with a summary of the laws of motion. And we've only covered the first law, so the other two, this is sort of a preview, okay? But one thing I want to just emphasize time and time again is that Newton's laws, as we're going to describe them here, as you'll see in these, this sort of bullet point summary, are only valid in inertial reference frames, okay? Strictly speaking, none of this is true unless we're in an inertial reference frame. And in most situations, we can treat Earth as an inertial reference frame. So just let's make that statement at the outset. Okay, so what's the first law? The first law says an object is going to move at constant velocity unless acted upon by an unbalanced force. We've already seen that. The second law is basically the famous F equals ma equation, okay? And we're going to get into the second law in just a minute here. But what the second law is saying, if we want to put it in words, is that it's the net force. It's the sum total of all the different forces acting on an object that determines the way it's going to accelerate, okay? Because if F net is the sum of all forces, and that's equal to m times a, what we can do is typically just solve for a by dividing out the mass, or m, for the object, okay? So the total force determines how something's going to accelerate. That's the second law. Okay, the third law. You may have heard of this statement before. For every action, there is an equal and opposite reaction. We've all heard that statement before. So that is, you know, sometimes used kind of metaphorically, of course, but it's also physically true. Whenever you have two objects that are interacting with each other, they exert forces on one another. The point is, force is not a one-way street. I cannot exert a force on something without that object exerting a force back on me. So let me give you a really easy example, right? I push the wall. Guess what? It's pushing back on me in the opposite direction. I'm pushing the wall this way. It's pushing back on me that way. Every single force works that way. It comes in pairs. Equal in magnitude, opposite in direction. That's the third law. Okay, so that's a summary of where we're going. Any questions so far? Okay, so I'm going to move a little quickly, and just as a note, what we're going to do for this first lecture involves a lot of text on the slides. Don't feel the need to copy down every single word, because remember, the slides are available on Canvas. So yeah, let's just keep it moving. So now we're going to get into the second law of motion. Okay. So in order to introduce the second law of motion, we're going to look at two experiments using forces that you could conduct. Okay. We're actually going to do something kind of like this in lab, I think 2 weeks from now. So here's the first experiment we can imagine. Something really simple. We're going to pull a block across a frictionless table, and as we pull the block, we're going to connect it to a spring scale. So this might be something like what you see in the grocery store to weigh your produce. It's just a scale that the more force we apply to it, the more the spring stretches out, okay? And so we're going to pull that, and we're going to do that to apply a force to the block. Then we're going to have a motion detector at the other end, and we're going to just use that to measure the acceleration of the block, right? So we apply some force, and then as a result, the block accelerates at some rate. That's what's going on here. So in the first experiment, let's imagine we do this several times, and we keep the mass constant. So that just means we're going to use the same exact block every time. We're not going to increase the mass. We're not going to decrease it. But what we are going to do is we're going to increase the amount of force we use. So first, we're going to pull with a very small amount of force, then we're going to increase it and increase it further and further. What you'll see happen is that the acceleration increases as you increase the force. That should be pretty intuitive. Of course, the more force we apply to the block, the faster it will accelerate. But the thing to notice is the exact relationship is a direct proportionality, okay? Acceleration increases directly proportional to the force, okay? So what does that mean? It means if we were to double the force, we'd get double the acceleration. If we were to triple the force, we'd get triple the acceleration. So the relationship between force and acceleration, super simple. They're directly proportional to one another, okay? Let's imagine a slightly different experiment, okay? So it's the same setup. We have the motion detector. We have some blocks on the table, and we pull the blocks using a spring scale so that we can measure the amount of force that we're applying, okay? But in this experiment, let's imagine that we keep the force exactly the same each trial. So I can just look at the scale and make sure I'm not changing the force. I'm just hitting the same exact target value for that every single time. But what we are going to change is the mass. So, I don't know, maybe I have a whole bunch of these blocks. They're all the same, right? So I'll start with one block, and then I'll chain two of them together, and then do 3 blocks, 4 blocks. That's how I can increase the mass, right? Here's the result. The acceleration is going to decrease as I increase the mass, right? If I keep the force the same, but I'm trying to pull more mass, well, I'm going to get less acceleration. That should be fairly intuitive, right? So less acceleration as we increase the mass. And to be more specific about that, acceleration and mass, it turns out, are inversely proportional to one another. So force and acceleration are directly proportional. Mass and acceleration, inversely proportional. So what does that mean? If we just double the mass while keeping the force the same, we would be cutting the acceleration in half. Okay? If you were to triple the mass, you'd be cutting the acceleration down by a factor of 3. Okay? So this is just empirically true. You're going to verify this in the lab. But for now, let's just take it for granted that this is how it works if you were to do this kind of experiment. Okay? So hopefully that's all pretty intuitive. So how can we wrap this all up into a nice, concise statement about how force, mass, and acceleration all relate to one another? Well, it's basically encapsulated in this equation right here, which says F equals ma. Experimentally, remember, acceleration is proportional to the total force and inversely proportional to the mass. So we want A to be directly proportional to the force, and we want it to be inversely proportional to the mass. So imagine you divide out the m in this equation. You'd see there's that inverse proportionality. And that's the statement of the second law. The net force, the sum of all the forces acting on an object, equals the mass of that object times the acceleration of that object. Okay? So with that said, let's do a little bit of dimensional analysis in the second law, okay? I want us to look at all the terms in the equation, the force, the mass, and the acceleration, and just ask the question, what type of quantity are we dealing with here? And what type of unit might be associated with that quantity? So let me ask you this: acceleration. What do we measure that in the SI system typically? What unit do we use? Yeah, acceleration, we typically use meters per second squared, right? But more generally, in terms of dimensions, that's a length divided by a time squared. You could use any unit you want for length and time. Okay, what about mass? What unit do we typically use for that? So it turns out in the SI system, it's kilograms is the fundamental unit. So kilograms is what we'll typically want to convert everything to, just as a side note. But it's a type of mass, right? So on the left-hand side, we have dimensions of force. That's saying, when we put the little brackets around that, we're asking, what type of quantity is force? Well, it's just a mass times an acceleration, where a mass has dimensions m, and acceleration has length over time squared, so that's LT to the minus 2. So whatever force is, it has these dimensions. That's the point. And if we use our traditional units for the SI system, remember, mass units are going to be kilograms, length units are going to be meters, and time units are going to be seconds. So we have kilograms times meters per second squared. This is how we break down force into these fundamental units. But typically, we're not just going to write this whole thing out anytime we have a force. Instead, this is going to be given a special name. This is what we call a Newton of force. So 1 kilogram times a meter per second squared is by definition a Newton of force. And that's going to be our fundamental unit that we use in the SI system. Okay? So any questions on how this works with the dimensional analysis? All right. So let's keep going with this. I want you to think about this situation here, okay? You have two blocks. Block 1 has mass m, and it's being pulled in two different directions with a force 2F and then a force F this way. So I'm not giving you actual values for m and F, but it's all symbolic, right? The second block has double the mass, so we'll say it's 2m, and it's being pulled this way with a force 3F, and it's being pulled that way with a force 2F. So my question for you is, how do we compare the two accelerations? Okay, are they the same? Does block 1 have a bigger acceleration, or does block 2 have a bigger acceleration? So what I want you to do is, at your desk, just work out F equals ma for each one of the blocks. Remember, we have to add up the two forces to get the net force. And then just solve for the acceleration, and you'll be able to tell me which one is bigger. Okay? So try to work it out, see what you get. We'll go through it together in a few minutes. And in the meantime, while you're working on that, raise your hand if you did not get the test back. Has everybody? All right, what do we think about this? Who says block 1? Block 2? Same acceleration? Okay. A few people answered C. So yeah, most of you got this correct. It's block 1. Let me just show you real quick how I would tend to think about this one. So for block 1, we're going to just apply F equals ma, which means we're going to sum up the two forces. Okay? Now here's how it works when you have two forces that are going in exactly opposite directions. You can just subtract them from one another. So I have 2F going to the right minus F going to the left. That's how I would sum up the two forces in direct opposition. And then I would just say that's equal to M times A1. So remember, this block has just mass M, so that's what I'm using here. Well, this net force is just F, so 1 unit of force to the right is what we get. So A1 is just F over M, whatever those numbers happen to be. For block 2, do the same thing, apply F equals ma. Now for this one, we have force 3F going to the right, and then force 2F going to the left. But now, the mass we're going to plug in is 2M, so it has twice the mass. And notice that the net force is exactly the same, right? We add the forces together, we get the same value as before, but now we have on this side 2M times A2. So A2 is equal to F divided by 2M. So in other words, for the same exact net force, the one that has less mass, which is this one, is going to accelerate at a faster rate. Okay? Does that make sense? All right, then. Let's keep moving. So here's another one that I want you to work on at your desk. Try this out. So let's say we have a 300 kilogram box, and what we're trying to do is accelerate it from rest. So we're going to start with 0 motion for the box, and we want to get it up to a speed of 3 meters per second, and we want to do this within 10 seconds. Okay, so from this you can calculate what the acceleration would have to be. That's a hint. Okay. But what I want you to figure out is how hard would you need to push the box? In other words, what force would you need to apply to it, measured in newtons, in order to get it to accelerate like this? So you can assume there's no friction. So the only force that you really need to consider that's acting on the box is the force of your push. That kind of simplifies things. Okay, so get the acceleration, plug it into F equals ma, and that will tell you what the force that's necessary is. So try it out, see what you get, and then we'll go through it together. Okay, so I see a number of you have this. Just go through it real quick. So again, the first thing we're going to do is calculate the acceleration. And here I'm just going to figure out what the magnitude is. Of course, we're accelerating to the left in this problem, but just in terms of the magnitude, this is delta V over delta T. It's our change in velocity divided by how long it takes to undergo that change. Remember, this is the definition of A. Okay, what's our change in velocity? Well, we end up at a speed of 3 meters per second, so that's our final value. And we start at 0. We start from rest. And then the time interval is how many seconds long? It takes 10 seconds to do this, so that's 0.3, right? Meters per second squared. That's our acceleration. So the net force acting on the box equals m times a. And what we're assuming here is the net force, because we don't have any friction or anything impeding the motion, is just equal to the force of your push, which I'll call P. And that's the mass of the box, which is 300 kilograms times 0.3 meters per second squared. That's our acceleration. So again, this would be a little bit more complicated if we had to account for friction, but for now, this is just how it goes. And what do we get numerically for this? We get 90, right? And take a look at the units. We have kilograms, meters per second squared. What do we call this again? Newtons, yeah. So we have 90 newtons of force. Okay? It's a bit unrealistic because in the real world, you're going to have to be fighting against friction, so you'd have to push it a lot harder than that. Okay? All right, so let's now talk about how to deal with F equals ma in vector form. Okay, so F equals ma is a vector equation. This is really important to remember. Acceleration, we already saw in the last chapter that this is a vector. Okay, it can be expressed in terms of x, y, even z components if you're working in 3 dimensions. And force is also a vector, right? The direction that you apply a force is something that's relevant. So one thing just to notice right away is that we have a vector f and we have a vector a, and multiplying the vector a is just a mass, right? What kind of quantity is mass? Is that a vector or a scalar? Yeah, that's just a scalar, right? Mass doesn't have a direction. It makes no sense for me to say, the stapler is 1 kilogram east, right? That's meaningless. So this is just a scalar, and as it turns out, mass is always positive too, right? So remember what happens when you multiply a vector by a positive scalar? You just get something that's pointing in the exact same direction, okay? So that is to say, the net force, the sum total of all forces, is in the exact same direction as your acceleration. That's something to just see about the way this equation works, okay? But another thing we can do is take this equation and break it down into components. So I'm going to take the left-hand side of the equation, the net force, and I'm going to write it in x, y, z form. Okay, so this is how that works. For the x component, what I'm doing is I'm taking the forces only in the x direction and adding those all together. So add all the x components together and then multiply by I hat. And then this says add all the y components together, multiply by j hat, and then add all the z components together, multiply by k hat. That's how we can really expand this out into x, y, and z, okay? On the other side of the equation, we have ma. Right, so it's m times vector a. Remember, vector a can have an x component, it can have a y component, it can have a z component, right? So expand this out, it can say ma equals max, we're just picking up the x component there, times I hat, plus may times j hat, plus maz times k hat. So all we did is we took the original equation, F equals ma, and then expanded out both sides in terms of x, y, and z components, okay? But what you should notice here is that we can group things together, okay? I can group together the x components because they both multiply I hat. I know that this side of the equation and this side of the equation have to be equal to one another. Same with the y components, right? Because they both multiply j hat. I know that this side of the equation and this side of the equation have to equal each other. And same with the z components. So what I'm really saying here is, if we're working in 3 dimensions like this, x, y, and z, F equals ma is actually 3 different equations. One for the x direction, one for the y direction, and then one for the z direction. Okay, so this is our actual set of 3 equations, one for each direction. Let's be clear about what this is saying. This says, add up all the forces in the x direction, you get m times the acceleration in the x direction. Add up all the forces in the y direction, you get the mass times the acceleration in the y direction. And then same thing for z. Now in this class, we're typically going to just be working in 2 dimensions with x and y, but I want to show you it easily extends to 3 dimensions, okay? So this should be a familiar idea because we have a vector equation. We can always break it down into components, okay? We've seen this kind of thing before. Okay, so with that sort of thing in mind, let's do an example. So this one, I'll just show you how it works out on the slide. Here's what's going on. We have 3 velociraptors that are fighting over a meal, and the mass of that meal is 2.5 kilograms. The first raptor pulls on the meal due south with a force of 85 newtons. The second raptor pulls with a force of 90 newtons in a direction 35 degrees north of east. And what we know is that the meal accelerates due north at 20 meters per second squared. So the question then becomes, what is the magnitude of the force that the third raptor is pulling with? So this is just an F equals ma problem, because when we take these 3 different forces and we add them together, we get mass times acceleration. We know something about 2 of the forces. We know the mass and we know the acceleration. So we can use that to find out something about the third force, the unknown one. And so we're going to break this down into components to solve the problem. All right, so we're going to start with this, a coordinate system. So the x direction is going to correspond to east, and the y direction is going to correspond to north. That's the coordinate system we'll use. And then the thing we'll do next is draw what's called a free body diagram. Remember, I told you what a free body diagram is before, but let me just tell you again. This is a diagram where we show all the different forces that are acting on the object. So in this case, we have the 3 different forces, which I'll call F1, F2, and F3. So remember, the first raptor, let's read the text again, is exerting a force due south. So that's F1. The second raptor is pulling in this direction, 35 degrees north of east. So that's kind of in the first quadrant like this. And then the third raptor, we don't know what the force that's being exerted is, but we'll just call it F3, and we'll leave it as an unknown for now, okay? So let's take a look at the information we've been given, okay? The first thing is the mass. It's given right here. The mass is 2.5 kilograms, so that's m. We're also given the acceleration. Right here it says the acceleration is due north at 20 meters per second squared. So what I'm going to do is write that as a vector in xy form. So remember, if we're moving due north, that means we're not accelerating at all in the x direction, right? So for the acceleration, I'm going to say 0 times I hat, and then plus 20 meters per second squared times j hat. That's how I can say I'm accelerating due north. Okay, let's think about force number 1. You can just see from the diagram that force number 1 does not have any x component, right? There's no part of this force that points east-west, right? It's just pointing straight south. So for this first force, we're going to say 0 I hat once again, and then minus 85 newtons j hat because we're going in the minus y direction if we're pointing south. Make sense? Okay, for the second force, F2, This one, if we want to write it in XY form like this, we're going to have to do a little bit of work, right? So remember, we have an angle, 35 degrees. It's measured off the x-axis in the sort of standard way. And we also know the magnitude. So if I take the magnitude of this force times cosine of the angle, that gives me the x component. So here what we have is F2 equals 90 newtons. That's the magnitude of the force times cosine of 35 degrees. That's our angle. That's going to be our x component. So I'm going to multiply that by I hat. For the y component of that force, I'm going to have 90 newtons times sine of 35 degrees. And that's multiplying j hat because that's our y component. Okay? So this is just what's in the text of the problem. Is it clear how I was able to write this all down? Okay, so the idea is we don't know F3. Let's figure out what that is. We'll use F equals ma to do that. Okay, so the way we're going to actually do this, you don't have to do it this way, but for the purposes of this problem, we're going to break everything down in our F equals ma equation into an x equation and a y equation. So when I do that, I'm going to solve for the x component of that force and the y component of that force as separate things. And then later I'll put them together to get the magnitude. Okay? All right, so that's the given information. That's our free body diagram for reference. So now we're going to apply Newton's second law in both directions, x and y, using vector components. So the net force in the x direction. Does force number 1 have an x component? No, we said that before, right? Does force 2 have an x component? Yeah, we did work it out. Force 3 also has an x component, right? For our acceleration, do we have an x component? What's ax going to be again? That's going to be 0 because we're not accelerating in this direction. We're just accelerating straight north, right? So that first equation, if we break it down, says, okay, there's nothing to put in for F1. So we're just adding these two x components, which are 90 cosine 35 degrees for the x component of F2. For the x component of F3, I don't know what it is, so I'm just going to write that as F3x. Okay? And that equals 0, because we're not accelerating in the x direction. Okay, this is what happens when we take a look at the y equation. Okay? So for the y equation, I'm going to add up all the y components of my forces. Okay, so for F1, remember, that's minus 85 newtons, because we're pulling straight down with a force of 85 newtons. For F2, my y component, as we worked out earlier, is 90 times sine of 35 degrees. And then for the y component of F3, we do not know what it is, so I'm just going to put that as a variable, F3y. All right? And that equals m times ay. That's the mass, which is 2.5 kilograms right here, times the acceleration in the y direction, which is 20 meters per second squared right here. So is everybody clear on how I got this equation and this equation? Okay? So I'm going to spare you the algebra. It's pretty straightforward to do. You can just solve for F3x using the first equation, and then you can directly solve for F3y using the second equation. Just punch those numbers into your calculator, and you'll see it works out like this. F3x is minus 73.7 newtons, and F3y is 83.4 newtons. So, by the way, it kind of makes sense that this x component should be negative, right? Because overall, we're not accelerating in the x direction. That means in the x direction, the forces must be balanced out. So if there's a force pulling in the positive x direction like this, it has to be balanced out by something pulling in the negative x direction like this. Okay, and that's what we found. So if I have these two components, how do I get the magnitude of the force, which is what we're being asked to find? How do I get the magnitude?
Square and take the root.
Yep, so force works just like any other vector. If you have the x and y components, you take the square root of x squared plus y squared, and that's the magnitude. So, the magnitude of the force, which we write as F3, with the vertical bars around it, that's the magnitude of F3, is the square root of F3x plus F3x squared plus F3y squared, like this. So just plug these numbers in, and tell me what you get. Can someone try that out? Plug in the x and y components, and see what the magnitude comes out to.
111.3.
I'm getting 111.
Oh, yeah, that's what.
Oh, sorry. I misheard you. I thought you said 101. Okay, good. So we're on the same page. 111 newtons. All right? Any questions? And of course, we could find the angle if we wanted to also, using this. Right? How would that work? Yeah, I could use the inverse tangent, plug in the x and y components, and I can get the angle as well. Okay? Yeah?
I'm a little confused on why you didn't put 20 meters per second squared times 2.5 on the x direction when you said it equals.
Because we're not, okay, this is important, we're not accelerating in the x direction. So ax itself is equal to 0. So I'm really just saying the mass times 0. Yeah? Okay? All right, we're going to do one last example here. It's another F equals ma type example. A lot of the upcoming homework is like the example I just showed you and this one. Okay, so let's see what's going on. Here is a 18.5 kilogram object, which is on a tabletop with no friction. So imagine something like an air hockey table to see how this would be going. There are two forces that are acting on it, which are F1 and F2. And we're going to assume that these are just constant forces. They don't change over time. Okay? So F1 has a magnitude of 1.2 newtons. F2 has a magnitude of 16.0 newtons. And the angle between them is 120 degrees. But we see F2 is just on the y-axis like this. Okay? And there's a 120 degree angle between them. So there's a number of things we're going to do here. First, we're going to find the acceleration of this object. We're going to find both the magnitude and the direction of that acceleration. You can probably see how this is going to go. We're going to add the two forces together. That's the net force. And then using the mass, we can solve for the acceleration. Just using F equals ma. And then here's a follow-up to that. Let's say that at t equals 0, the object is at the origin. So it's at x equals 0, y equals 0. And it's also at rest. And then the question is, let's say 2.5 seconds later, where is it going to be located and how fast is it going to be moving? So the idea is, if it starts off like this at rest, but we apply these forces to it, it accelerates. And because it accelerates, it's going to move somewhere else, and it's going to be moving at some speed by the time 2.5 seconds passes. Okay? So we'll be able to actually use kinematic equations to do this second part. Okay, so let's just write down what we know about these forces. We know the magnitude of force 1 is 1.2 newtons. We know the angle of force number 1. What can we say about the angle of force number 1 if we measure it off the x-axis?
-3.
Yeah, we could say this is negative 30 degrees, or we could say 330 degrees. Either one is fine. The point is we have to indicate that we're in the fourth quadrant with this force. Does that make sense? Okay. For force number 2, this one has a magnitude of 16 newtons, and it's angled relative to the x-axis. What is the angle? Yeah, this one's at 90 degrees. So let me just draw this out, right? If this is the x-axis, this is force 2, and this is force 1. So that's how we measure those angles relative to the x-axis, shown here. Okay, so let's do this. Let's calculate the net force. F1 plus F2, those are the only two forces that we need to think about. So those are the two we're adding together when we calculate the net force. And these are vectors, okay? So when I add them, I have to treat these like vectors. I'm not just doing 1.2 plus 16. It's not that simple, right? I have to break each one down into components and then add it. So let's do that. So for force 1, I have 1.2 newtons cosine of minus 30 degrees times I hat. That's the x component of force 1. Plus 1.2 newtons times sine of negative 30 degrees. That's the y component of that force. So it comes with the j hat unit vector. For force number 2, okay, what's the x component for force number 2? This is the one that's pointing just in the y direction. 0, right? If you do cosine of 90, you'll see it comes out to 0. So that's y. Okay? What's the y component? Well, it's just 16.0 newtons, right? If you have a force like this that's just pointing along some axis, every component is 0 except for whichever axis it's pointing along, in which case that would be the magnitude. Okay? So if it's all in the y direction, this is how we express that idea. Okay? Okay, so you add these together, you're going to find that it comes out to 1.04 newtons I hat plus 15.4 newtons j hat. So for the net force, those are the x and the y components. Okay? So we have the net force equals mass times acceleration. If we want to solve for acceleration, just divide the mass, right? Just do 1 over m times the net force, and that's your acceleration. Okay? So in this case, our mass was 18.5 kilograms, and then the net force is what we just calculated here. So it's 1.04 newtons. Now remember, what is the equivalent way to write newtons out? It's kilograms times what?
Meters per second squared.
Yeah. So instead of newtons, I'm going to write this as kilograms times meters per second squared. And then we have I hat, and then we have 15.4 newtons, which is also kilograms meters per second squared times j hat. Does that make sense? Notice how kilograms cancel out. Here and here. Okay? So therefore, we're in just meters per second squared. We have acceleration units, right? So for the x component, here's what I'm doing. I'm taking 1.04 divided by 18.5. And if you crunch those numbers, you'll find it comes out to 0.0562 meters per second squared I hat. And then for the y component, I'm taking 15.4 divided by 18.5. And if you crunch those numbers, you'll find it comes out to 0.8324 meters per second squared j hat. Okay? So to be clear, what we just did is we used F equals ma to find the x acceleration, ax, and the y acceleration, ay. All right? So to be clear, we found a vector A for acceleration, where this is ax and this is ay. What we want to do now is find the magnitude of this vector, so just how fast are we accelerating, and then the direction. What direction are we accelerating in? So the direction would be this angle here, which I'll call theta. The magnitude will just be the length of the vector. So at this point, it's just like any other vector, right? If I want the magnitude, what do? You tell me.
Square them, square root.
Square them in square root, right? That's a really concise way to say it. I like that. So a magnitude equals square root ax squared plus ay squared, right? We found out what these x and y components are, so we're going to plug them in. Ax came out to be 0.0562 meters per second squared. Square that. Sorry, that's ax. Ay came out to 0.8324 meters per second squared, and we'll square that, and then we'll root the whole thing. Okay? And this comes out to, let me just tell you the result, you can verify this. This comes out to 0.834 meters per second squared. So that's the magnitude of our acceleration, okay? Okay, how do I get the angle for my acceleration vector? If I know the x and y components and I want to know the direction, how does that work again? So here, I can say tangent of my angle. Tangent is the opposite side, which is AY, divided by the adjacent side, which is AX. So I can say tangent of my angle is AY over AX, which means my angle is the inverse tangent of AY over AX. And for that, we're going to plug in the values once again. We have tangent inverse. AY is 0.8324. AX is 0.0562. Right? And the units will just cancel out, so I'm not even going to write them. Can someone tell me what this works out to?
86.1 degrees.
So it's like 86 degrees. I've been following the sig figs. I don't have a lot of time to explain the details of that, but we're around to 2 here, okay? And we know all the information about the acceleration that we could possibly know, right? We found the x and y components, and then we also know the magnitude and the direction, okay? So now, the last thing we're going to end with is I can actually use that information to find position and velocity. See, what Newton's laws allow you to do, what dynamics allows you to do, is to calculate an acceleration if you know the forces. But kinematics allows you to take that acceleration and calculate position and calculate velocity. Okay? So remember our kinematic equation for position. That goes R equals R naught plus V naught T plus 1/2 AT squared. And remember, we can take this and break it down into an x equation and a y equation. My x equation is just x equals x naught plus v naught x times time plus 1/2 ax t squared. Now remember 2 things. We start at the origin and we start off at rest. So what's the value of x naught? This is going to be 0 because we start at the origin. Right? X coordinate is 0 to start off. What is this going to be? V naught x. That's going to be 0 as well. So here, x naught is 0 because we start at the origin. And v naught x is going to be 0 because we start at rest. Okay? So I'm really just dealing with the 1/2 AT squared part. So here's what I have. I'm going to plug in the x acceleration into my x equation. So that's 0.0562 meters per second squared. And then I'm going to plug in my time, which is 2.5 seconds. The question asks, at 2.5 seconds, what is the position? So we square that whole thing. Now what this works out to is 0.18 meters, if you crunch those numbers, okay? Now remember, we can do the same thing with the y equation, which says y equals y naught plus v naught y times time plus 1/2 ay t squared. So let's just run through this real quick. What am I plugging in for y naught?
Maybe 0.
0 again, because we start at the origin, right? That's for x and y. What do I plug in for v naught y? Still plugging in 0. We start off at rest. That means we're not moving in the x or the y direction. So the initial y velocity, that's what that means, is going to be 0. Same reasoning, right? Okay, then I just have 1/2 times ay t squared. Ay is what we calculated over here. That's 0.8324 meters per second squared. That's multiplying t, which is 2.5 seconds squared. If you crunch these numbers, you will get 2.6 meters. So that means the position of our object at the time in question is this. 0.18 meters on the x-axis, 2.6 meters on the y-axis. That's our final position. Does anyone remember the velocity equation for final velocity? Because that's what we want to know. We also want to know the velocity. How does this work? Yeah, so v, that's our final velocity, equals v naught. That's our initial velocity plus at, plus acceleration times time. Okay? I want to do this in kind of a shortcut way. Okay? What can I say about v naught? 0. So this just means v equals at, correct? Let's say I just want to know the speed. The question is just asking us about speed. How fast are we moving, okay? Speed is the magnitude of velocity. So if I take the magnitude of both sides, then I'll be calculating the speed. You see that? Okay. So this is the magnitude of the acceleration that we found times time, just to get the speed. If I wanted x and y separately, I'd have to write a separate x and y equation, but if I just want the speed, I can just do this, okay? So what's the magnitude of my acceleration? That's this part. We found it earlier. It's up on the page. What's the number? That's this number we calculated, 0.834. Meters per second squared. And then we multiply by the time, 2.5 seconds. And what we get is 2.09 meters per second. So to summarize, we used F equals ma to solve for the acceleration. As long as we know what the forces are, we can get the acceleration. And then we can use that acceleration in our kinematic equations that we've seen before to figure out, to make a prediction basically about how the object is going to be moving at some time later. That's what Newton's laws are all about. You can predict how something is going to move at any given time as long as you know the forces and the starting motion. Okay? So that's it for today. I'll see you in lab if you're in the Thursday lab. If not, I'll see you on Tuesday.